Hello students, in this video we'll see an example of computing determinants whose elements form an arithmetic progression. Let's consider first a simple matrix. Consider the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. I claim that the determinant of this matrix is equal to 0. So let's call this A sub 3. Then this implies that the determinant of A sub 3 is equal to 0. I'll show this in two ways. The first way is a clever trick. The trick is the following. If I look at 1, 2, 3, 4, 5, 6, 7, 8, 9, and I input this vector 1, negative 2, 1, what's going to happen over here? I'm going to have a 1 minus 4 plus 4, that's 0. I have a 4 minus 10 plus 6, that's 0. And then a 7 minus 16 plus 9, that's 0. And that implies that lambda equals 0 is an eigenvalue with eigenvector 1, negative 2, 1. And of course, if I get a 0 eigenvalue, the matrix is invertible, therefore the determinant is 0. That's one elementary way to do it. Another way to do it is I can subtract alternatively, subtract column 2 from column 3. And column 1 from column 2. If we do that, what will we get? We'll have the following. So if I subtract, so column 1 is going to remain the same. And then if I subtract column 2 from column 3, I'll have a 1, and a 1. Column 1 from column 2, a 1, and a 1. Right? And of course, there's two columns that are the same here, so I can do column 2 from column 3, reduce row, so I'll do a negative of column 2 plus column 3. That will give me a 1, 4, 7, 1, 1, 1, then a 0, 0, 0, and therefore we get the determinant of this matrix, determinant of A3 is equal to 0 in yet another way, right? So of course this might have been a coincidence, 1, 2, 3, 4, 5, 6, 7, 8, 9 gave me a 0 determinant, but let's do the same thing with the next dimensional up, right? So let's look at this matrix now. Consider A4, which as you expect will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 over here, okay? That's the next dimensional square matrix where I have the first squares in there. Right now, you may say, well, how am I going to figure out what this determinant of A4 is? We claim, so claim determinant of A4 is also equal to 0, right? Well, now, of course, you can see sort of the same sort of structure over here. If I do column 3 minus, if I do column 4 minus column 3, I'll get all 1s. If I do column 2 minus column 3, I'll get all 1s. If I do column 1 minus column 2, I'll get all 1s. So in other words, we can see this by the following. I can replace column 4 can be replaced with column 4 minus column 3. That won't change the determinant. Column 3 will be replaced with column 3 minus column 2. That won't change the determinant. And then column 2 will be replaced with what? Well, actually, that's all I need to do over here, right? I can, for the sake of argument, I can say column 2 gets replaced with column 2 minus column 1. Then I have 3 columns of all 1s. So we get 3 columns of all 1s. This implies 3 columns. Actually, we only need 1 of all 1s. And that means the determinant of A4 is equal to 0. Okay? Of course, I can do the same sort of eigenvector trick over here. If we look at our matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If I look at the vector over here, 1, negative 1, negative 1, 1, what are we going to have? Well, we'll have a 1 and then a, let's see, a 1 and a 4 gives me a 5, and a negative 2 and a 3 gives me a 0. Then I'll get a 5 and an 8, that's a 13, minus 13, that gives me a 0. And then what? And then we're going to have a factor of, let's see, we'll have a 9 and a 12, that's a 21. Oh, negative 21, 0. And then finally we'll get a 13 and 16, that's a 29. 29 gives me a 0 over here. And that says that this vector 1, negative 1, negative 1, 1 is an eigenvector with eigenvalue 0. and that implies that the determinant of A4 in another method is equal to 0. And so in some sense, we see this method is fairly robust, right? If I have an arithmetic progression, what can we say? If I look at the last column, and so from the last column, what I'm going to do is I'm going to take that last column and I'm going to subtract off the last column minus the column before it to give me a column of all ones. Then I'll do the column before that, and then I'll say that the n minus first column minus the n minus second column is going to be a column of all ones. So I have two columns of all ones, and I can reduce that last column to be a column of all zeros. Once I have a column of all zeros, I know the determinant is going to be equal to 0, right? So in general, we can prove that the determinant of an is equal to 0, where what is an? An is the square matrix that looks like this. Looks like 1, 2, up to n, then n plus 1, down to 2n, then 2n plus 1, down to 3n, all the way down to n times n, right, which is n squared, right? This determinant will be equal to 0 by the same exact reasoning, because I'm going to have an n minus 1 over here, then I'm going to have a 2n minus 1 over here. So if I subtract those things from each other, I'm going to get a 1, 1, 1, 1, 1, and do the same procedure over again. You'll get all 1s in the last column. And once you have all 1s in the last column, the second to last column, you subtract those things, you get a column of zeros, which will prove the determinant is equal to 0. So these determinants, this whole family of determinants, are equal to 0. The only catch, of course, is that n has to be bigger, strictly bigger than 2, because if we have n equals 2, for example, we'd have what determinant? 1, 2, 3, 4. We'd have a 4 minus 6. 4 minus 6 is negative 2. So this pattern only works when there's at least one extra column for me to sort of turn into 1. So in other words, once you're past n equals 2, all of these determinants are equal to 0. Thank you very much.